All right, welcome one, welcome all. How are you guys today? I am glad to hear it. I hope you guys are well. I hope this does nothing to change that. Let's see. So, today I wanted to talk about fluid mechanics. Um, so, the definition that we're going to use for a fluid is a collection of molecules that are randomly arranged and that are also held together by weak cohesive forces and also by the walls of the container. For our purposes, a fluid will either be a liquid or a gas. Um, so hopefully this is okay. Um, I'm going to return us to our definition from earlier in the semester of what we meant by pressure. And pressure, I'm just going to define to be the force per area. Um, we could say that uh, the incremental bit of force is equal to the pressure times the incremental bit of area. Um, the unit of pressure that we will use in our SI MKS system is the Pascal, and it is just defined to be 1 Newton per square meter. So let's talk about fluid pressure as a function of depth. So um, if we have some container of water, like a cup or a beaker, we could uh, just pick some little volume of the fluid. Um, let's go with water, just because I think it's a familiar fluid to us, right? We could pick some little volume of water, and here I've shaded it in. Um, and if this is still water, then uh, it has some volume that is defined by its height h and its cross-sectional area a. If it's still water, then this little volume of water isn't going anywhere. And so in that case, the sum of the forces acting upon it must needs be zero. And so we could say that the sum of the forces is zero, and there is some pressure force pushing up. There's also some pressure force pushing down, and there's also the weight of that volume of liquid. Now, I want to be careful here and tell you that pressure is not a force, but since pressure is the force per area, you can get to a force related to the pressure acting across some area, right? The other thing that I want to point to is that pressure is not a vector, in that uh, pressure acts in all directions. It doesn't have a specific direction. And so at the top of this uh, volume, the pressure is going to push down. At the bottom of this volume, the pressure is going to push up. And along the sides, it's going to point inwards uh, against the surface. Hopefully that's okay. But if we know that the pressure acting against the bottom surface minus the pressure pushing down against the top surface minus the weight, right? So notice that both the pressure pushing down against the top surface and the weight point in the same direction, right? That's what these two minus signs tell us. If those all sum to zero, then we also know that the mass of this section, this volume of water, is just equal to the density times the volume, right? We've been doing that for a while now. Um, then then we can say that, well, we know the volume of this, it's just equal to the height of this column multiplied by the cross-sectional area. And so the volume V is just equal to H times A. And so the mass is just going to equal rho times h times a, where rho is the mass density, the mass per volume. So in that case, we could rewrite this equation as the pressure against the bottom pushing up against the bottom surface A minus the pressure at the top pushing down against the top surface minus m times g, but we just said that m is equal to rho times h times a. So m times g is just rho times h times a times g. And they're all in acting in the j direction, right? The y direction. We can kind of manipulate this by bringing this weight term across the equal sign, and then we get that PA minus P naught A is equal to rho HAG. Notice that there is now an A in each term, and so we could say that the pressure at the bottom is equal to the pressure at the top plus rho GH. Hooray! This equation is going to be very useful to us. In fact, perhaps useful enough that we should give it, set it aside a little. So keep note of this one. We're definitely going to make use of this again. So if the liquid is open to atmosphere, in other words, this cup doesn't have a lid, we don't have to worry about that. And we just choose that P naught is the pressure at the surface of the liquid where H is going to be 0, then we're going to say that P naught is the local atmospheric pressure. And here at sea level, atmospheric pressure on average is about 1.013 times 10 to the 5 pascals. That's 101,300 pascals. And we're just going to define that to be 1 atmosphere. So just by definition, we're going to use this as atmospheric pressure. Let's look at Pascal's law then. So Pascal's law in words is that a change in pressure applied to a fluid is transmitted undiminished to every point of the fluid and to its container walls. So let's come back to this. Note that the pressure at the bottom is equal to the pressure at the top plus rho GH. So what this is telling us is that the pressure at the top is transmitted throughout, right? That's you can get to this Pascal's law just from this equation we just described. And I also want to take a second to do the following. So note that as we descend, the pressure is increasing. So I've tried to represent the pressure here by arrows, and notice that the length of the arrows is increasing with increasing depth. That's just because, as is noted in this equation, that the pressure scales linearly with depth, right? And so as you go deeper and deeper and deeper, the pressure goes up and up and up. Hopefully that's okay. Questions about that, please let me know. Okay, so here is kind of an example using Pascal's law. So it's a hydraulic lift, which is something that you see in a lot of garages. The way that this works is you're going to use some compressed gas to push down on the piston on this side, and there is some pressure medium in here. for our purposes, we could just treat this as a liquid, um, which since if you change the pressure anywhere, it changes the pressure everywhere. If you increase the pressure on this side, it will also transmit that same change in pressure to the opposite side. And um, so this can be used uh, to to gain a mechanical advantage to amplify a force. Um, and uh, so in this case, on this left side, the radius of the piston is 5 centimeters. On the right side, the radius of the piston is going to be 15 centimeters. And let's say that the weight of this car is 13,300 newtons. And we're going to just use compressed air to push down on the left piston. So notice that the left piston drops by some height, delta x1, and the right piston is raised by some height, delta x2. They have differing areas, A1 and A2. But what we can say is that I, since since our P1 has to equal P2 and P1 is just F1 over A1, we could say that F1 just has to equal A1 over A2 times F2, right? This comes about because since F1 over A1 is equal to P1 and F2 over A2 is equal to P2, since we're saying that if you change the pressure anywhere, it changes the pressure everywhere, whatever this change in pressure at the left column is also has to be the change in pressure at the right column. And so you can manipulate this formula to solve for F1. F1 is just equal to A1 over A2 times F2, right? Just multiplying across by A1. And we get to this. But A1, right, pi r squared, let's assume a circular cross section, and we said it had a radius. A1 is just pi times 5 centimeters squared, pi r squared. A2 is just pi times r2 squared, where r2 is just 15 centimeters squared. Remember the conversion between centimeters and meters, just divide by 100. And the weight of the car is 13,300 newtons, or 1.33 times 10 to the 4 newtons. What this tells us is that F1, the force that the air needs to push down with, is equal to 1.48 times 10 to the 3 newtons. That's only 1,480 newtons, right? Um, hopefully that's not terrible, right? Just carrying through this math. We could turn this back into a pressure. We could figure out what air pressure we're going to need. Air pressure is just going to be F1 over A1. Well, again, A1 is just pi r squared, and we just solved for what we meant by F1. And so if you carry through this little bit of division, then what you get is 1.88 times 10 to the 5 pascals. Now note that um, that the air pressure really only needs to be about, well, a little under 2 atmosphere. This is definitely something that you can get with an air compressor. So this is not an unreasonable value. So remember, the atmospheric pressure is about 1.01 times 10 to the 5 pascals. This is even less than 2 atmosphere, right? 2 atmosphere would have been about 2.026 times 10 to the 5 pascals. This is 1.88 times 10 to the 5 pascals. Totally within the realm of an air compressor. So let's look at pressure measurements. So again, we have some beaker with some liquid. This time we're going to invert uh, a graduated cylinder, tall although it must be, of the same carrying the same liquid into that beaker. Um, and what you would expect happens is that gravity is going to pull this liquid downwards, right? So that it leaves an evacuated region here where the pressure is basically zero. You might get some vapor pressure up there, but we're going to ignore that for our purposes. This beaker is open to air, and so it has an atmospheric pressure of P0. And so one way of thinking about what's happening here is that air pressure is pushing down on the outside, but there is also the weight of this column pushing uh, down on this liquid. When the weight of this column is equal to the weight of all of the air above, which is related to air pressure, then this will achieve a static equilibrium and this height will remain fixed. And so what we're going to say is uh, that air pressure needs to equal, and by the way, for this purpose, I'm going to use this liquid as mercury. And we're using mercury because mercury has a very high density. If we did this with water, we would need for this graduated cylinder, this long thin tube, to be very, very, very long. But in this case, we could say that atmospheric pressure is equal to the density of mercury, Hg is mercury, times little g times h, right? That's just our prior statement of pressure as a function of depth. And there's no plus p naught here because we're saying that uh, uh, the region up here is largely evacuated, right? You just took a full graduated cylinder of mercury and you turned it over into a beaker full of mercury. In that case, you can solve for h, the height of this column, and it's just going to be atmospheric pressure divided by the density of mercury and also divided by little g. Atmospheric pressure is typically about uh, 1.013 times 10 to the 5 pascals. The density of mercury is about 13,600 kilograms per cubic meter. And little g, you remember, is about 9.8 meters per second squared. Carrying through this division, you get a height of mercury of about 3/4 of a meter, 0.76 meters, or 76 centimeters. Now, if you were to do this with water, remember that uh, the the density of water is not 13.6 times 10 to the 3 kilograms per cubic meter. Instead, it's about 1,000 kilograms per cubic meter. And so the corresponding height, if you were to do this experiment with water, would have to be about 13.6 times greater than this, which is over 10 meters, right? Um, and so you would need a very, very, very tall tube to do this, a very, very tall straw. Um, this is how uh, many old-fashioned water pumps worked, um, where you just evacuate the tube above and allow air pressure to push water up the tube. It's also how you drink through a straw. Um, if you made the straw more than 13.6 times this height, then you would have a problem using the straw without adding to the air pressure. You would need something like an air compressor pushing down. let's look at a different kind of pressure measurement. Let's say that you wanted to know the pressure of uh, an enclosed volume of gas, like uh, in a glass container, or maybe even in the tire of your car or bicycle. Um, well, here you could hook this up to uh, a tube that is connected to the container you want to know the pressure of uh, on one side, and on the other side it's just open to atmosphere. And if you do that, then the absolute pressure of this gas is just going to be atmospheric pressure plus rho gh, where h is the height between uh, measured between the fluid on the open side and the level of the fluid on the gas side. So it is this height. Hopefully that's okay. That's the absolute pressure in here. Um, Typically, if you take a pressure reading, um, like for a tire, what you're actually going to get is the gauge pressure. And the gauge pressure is just a measure of how much above or below atmospheric pressure this enclosed region is. And so the way that we do that is we just subtract the P naught over the atmospheric pressure over to the other side. And so the gauge pressure tends to be a measure of the absolute pressure of the gas minus atmospheric pressure. So this is our gauge pressure reading, and it is just rho gh. Hooray! Okay. Let's look at buoyant force and Archimedes' principle next. So, um, so you've probably, if you've ever tried floating in a swimming pool, the buoyant force is the thing that holds you up. If you've ever thrown um, something uh, like a beach ball into a swimming pool and you noticed that it floated, or a piece of wood into a swimming pool, you've noticed it floated. Uh, what you've noticed there is uh, that there is a buoyant force acting upon it, right? And so we are going to describe this Archimedes principle is that the buoyant force, so the magnitude of our buoyant force, the magnitude of our buoyant force is always going to equal the weight of the fluid that is displaced by the object. And so here I've drawn our same beaker, and I've added a, a soda bottle. Um, what I want to point out is that the buoyant force pushing up on the soda bottle is the same whether the soda bottle is full of air or whether it's full of soda. In fact, the buoyant force is the same on the volume of water, even if there is no soda bottle, right? The thing that I would uh, tell you is that the magnitude of the buoyant force on the object is always equal to the weight of the fluid displaced by the object. So in this case, let's go back to the case of there is no soda bottle. Well, in this case, um, the that volume of where the soda bottle would be weighs as much as the volume that this is displacing, right? Because it is made of water, right? And so the buoyant force is equal to rho times v times g. Rho times v is just m, right? Remember that rho is m over v, so m is rho times v. So this is just the buoyant force of the weight of the fluid displaced, but it's being displaced by that very same fluid. And so in this case, if I look at the free body diagram, it's pulled downwards by rho vg, but there's also a buoyant force upwards of rho vg. And so this is in equilibrium, right? The sum of the forces is 0 in this case. Does that make sense? And so there is no incentive for this volume of water to either float up or float down because the buoyant force is equal to the weight. The buoyant force pushes up, the weight pulls down. If instead I take this region of water and I actually put a soda bottle filled with air there, well, now the buoyant force is the same, right? It's still displacing the exact same amount of water, but this time the weight of the soda bottle filled with air is very small. And so in this case, the buoyant force pushing upwards, I've drawn this vector large, but I've drawn the weight vector pulling down very small. So notice that this one is not in equilibrium. This one experiences an upwards force that will carry this to the surface. Hopefully that makes sense, right? It's just a free body diagram. If instead I fill this with soda, well, in this case, uh, the density of soda is about the same as the density of water. It's mostly water, right? Um, Notice that the soda bottle isn't filled all the way to the top. There's that little air gap. And so these are probably almost equal, but the buoyant force is possibly just a touch more. And so this will experience a very, very slight upwards net force carrying it towards the surface. Right? If if it turns out that the weight of this plastic bottle plus the weight of that air uh, in that uh, little enclosed space plus the weight of this soda, if that's exactly equal to the weight of the volume of water defined by this dashed line, because notice that the buoyant force is the same in all three cases. If that's true, then this soda bottle won't go anywhere. It's not experiencing any net force if the weight of this plastic bottle plus the weight of that air plus the weight of the soda is actually equal to the buoyant force, right? And so you could, this is an experiment you could do in your bathtub. If you have a soda bottle, um, uh, or uh, or like a pill bottle, something that you can seal well, so that it stays watertight. Um, if you put it underwater when it's totally empty, it's probably going to rise to the surface. And then you could slowly add water to it, or you could add sand to it, and you could find the point where uh, it has neutral buoyancy, where if you leave it at a depth, it will just sit there as long as you pull your hand away slowly. Um, uh, then you can actually put enough weight into this that the weight of the bottle, m times g, is equal to the buoyant force, rho times v times g, where v is the volume of the bottle and rho is the density of the fluid. So hopefully that's okay. You could try this. Take a bottle, uh, first try it empty, then add little bits of sand to it, making sure you seal it and it's watertight every time. Um, you could add enough sand to it that uh, that this thing will uh, will stay at a given height under the surface when you leave it. It won't rise or sink. If you put too much sand into it, then the weight is greater than the buoyant force. In that case, it has a net downwards force, and this thing will sink to the bottom. Okay, uh, let's think of our first case, totally submerged objects. In this case, uh, that it's, again, experiencing two forces, a gravitational force downwards, and the gravitational force downwards is the density of the object, average density of the object, times the volume of the object, times little g, and the buoyant force is equal to the density of the fluid times g times the same density of the object. And so this time we could write an equation of motion, right? It has the upwards buoyant force, the downwards gravitational force. So the gravitational force is defined thusly for a totally submerged object. The buoyant force is defined thusly. Notice in both cases here, it's the volume of the object that matters, because if it's fully submerged, the whole volume of the object is displacing water or whatever fluid you're talking about. So in this case, you could write your equation of motion as the density of the fluid times g times the volume of the object minus the density of the object averaged times g times the volume of the object. There's a gv object in both of these, and so we can factor that out. And what we get is that the quantity density of the fluid minus density of the object and quantity times gv object is equal to may. And here, the resulting motion of this submerged object is going to depend entirely upon the densities of the object and the fluid. If the fluid is more dense than the object, then the acceleration is upwards. It will float towards the surface. If the fluid is less dense than the object, then this value is negative. AY is negative 2. In that case, it's going to sink. So you might imagine taking a rock and throwing it into a swimming pool. The rock's density is greater than the water's density, and so it sinks. But if you took uh, uh, an empty soda bottle and you throw it into a swimming pool, well, in that case, the density of the object is less than the density of the fluid, and so this quantity in parentheses is positive, and so AY is positive. This thing is going to float to the surface. Hooray! So if you put an empty soda bottle underwater, um, plastic soda bottle underwater, sealed, it's going to float to the surface. But if you take a rock and you put it underwater and you let go, it's going to sink to the bottom. And that just has to do with which one's more dense. Is the fluid, in this case the water in the swimming pool, more or less dense than the object? If it's more dense, then the object floats to the surface. If it's less dense, the object will sink to the floor of the pool. The other case I wanted to explore is a floating object. As you probably can gauge from what we just talked about, if the object is floating, this already presupposes that the object's density is less than the fluid's density. In this case, we could say that the weight of the object, well, just like last time, right, is equal to the average density of the object times g times the volume of the object. The buoyant force is going to equal rho times rho of the fluid times g times the volume of the fluid that has been displaced. This time, unlike the last case where it's fully submerged, we can't say that the volume of the object is equal to the volume of the fluid displaced. If some of the object is sticking up above the surface of the water, then not all of the volume of the object is displacing water. And so in this case, we can say that the density of the fluid times g times the volume of the fluid displaced minus the average density of the object times g times the volume of the object equals 0. I can say it's equal to 0 once this thing is steady at the surface, once it's not kind of bobbing up and down. And so in this case, I can bring this term across the equal sign, And there is a g on both sides, so we can divide out. And we could say that the volume of the fluid displaced divided by the volume of the object is equal to the density of the object divided by the density of the fluid. If you take this equation, you can solve to get this statement. In fact, I would encourage you to pause the video now and convince yourself that you can solve this equation to get to here. Okay, so if you do that, all this is telling you is that the fraction of the volume of the floating object that is below the fluid surface will equal the ratio of the density of the object to that of the fluid. What this is, V fluid displaced divided by V object, that's just the fraction of the volume of the floating object that's actually below the surface of the fluid. Hooray! And it will equal the ratio of the object density to the fluid density. Let's let's look at a couple of examples because I like these. I think these are fun. Um, in fact, I often put some version of this into a conceptual question on exams, just maybe as further incentive to pay attention to this. Um, a single ice cube floats in a water glass. Uh, I'd like to know after the ice has fully melted, what's going to happen to the water level. And so what I'm saying here is you have this cup of water. It has a single ice cube floating in it. You're going to take a Sharpie or maybe a magic marker so that you're not, permanently uh, leaving a mark on your cup. But you're going to put a little mark here to note the water level when the ice cube is floating in it. And what I'm asking is, after this ice cube melts, is the water level going to go up? Is the water level going to go down? And I'm going to ask you to pause here and try and think about what's going to happen when this ice cube has melted. Okay, so hopefully you have a thought in your head about what you expect will happen. Gave it some good thought. Um, when the ice cube melts, this glass of water, the water level is going to be the same as before the ice cube melted. And I'm going to ask why. Well, the why here is because in order to float, this ice cube had to displace its own weight of water. It already pushed the water level up when you added the ice cube. Now, when the ice cube melts, well, it was made of water, right? The ice is just the solid form of water. And so it's going to fill in the space that it displaced, leaving the water level exactly the same against the side of the cup. Now, if you had noted what the water level was before you added the ice cube, that will be less. But if you take note of the water level once you've added the ice cube, and then take note of the water level after the ice cube is melted, you'll see it's still the same height. What does that imply about the density of the ice cube? Since some of it is sticking up above the surface, that tells us that ice is actually less dense than liquid water. Hopefully that's all right. So now let's slightly change this problem and let's examine what happens if it's not just an empty ice cube. This time it's an ice cube with a penny frozen inside of it. If you try this one, don't drink the water afterwards. Um, the penny is probably not super clean. Um, this time, if you start with a glass of water, you add an ice cube that has a penny frozen inside of it, and then you take note of the water level. So this is the water level when the ice cube with the penny is floating in the glass of water. Now I'm asking what's going to happen to the water level after the ice cube melts. And so again, I'll ask you to pause the video here and try and think through what's going to happen. Okay, so hopefully you gave this some thought. And so what I will ask you is, again, you have a glass of water. You, for whatever reason, froze a penny inside an ice cube. Maybe you wanted to check whether or not this lecture or video actually holds true to form to your experience. You add the ice cube with the penny frozen inside it to your glass of water, and then you mark the water level. So you come here with the glass of water, ice cube with penny frozen inside it. You you note what the water level is carefully. You have to, get down next to the glass and make sure um, that you're actually measuring this well, because the effect isn't huge for just a single penny. Um, so you're gonna have to be careful with this and make sure that you don't, spill water and stuff. Um, then you let this ice cube melt, and so what's gonna happen? Well, after the ice cube melts, what will the penny do? Well, the penny's gonna sink to the floor, right? It's gonna sink to the bottom of the cup. And so this time, what you'll see afterwards is that the water level has actually gone down when the ice cube melts. If you're just doing this with a single penny, it won't go down a lot. And so you have to be really careful with this experiment to make this work. Um, but uh, the water level goes down because when the penny sinks, it is only displacing its own volume of water. It is not displacing a weight of water equal to the weight of the penny. So, since the penny is more dense than the water, it is actually displacing less water when it sinks to the floor than when we were forcing it to float. Hopefully that's okay. Um, Pause the video here and convince yourself of why that would be true. You can do that entirely based on comparing case 1 up here to case 2. Okay, so fluid dynamics, we're only going to think of ideal fluids. I'll save for your later engineering courses the non-ideal cases. So for an ideal fluid, we're going to say that it is non-viscous. We don't have to worry about fluid friction. Viscosity is fluid friction. The flow is steady. Um, by this I mean that the flow lines of fluids aren't going to cross each other. We're going to assume that the fluid is incompressible, and we're going to assume that it's irrotational. We don't have to worry about little eddies. Um, so let's imagine that you have the following tube uh, resting on a table. So we are looking down above this side and this side are at the same height. So we don't have to worry about changing heights. Um, the fact that the fluid is incompressible means that if it's moving, right, moving through this pipe, uh, this fluid moving forwards means that all of the fluid in here also has to move forward so that we don't compress it. But since it's wider on this edge, in order for this to move delta x forwards, this moves a much smaller delta x2 forwards, which means that the two speeds are not the same. Um, if you kayak through or canoe through through rivers, you've probably noticed that when the river narrows, the speed of the water increases. That's that's what this is showing. And you can describe this mathematically as A1 times V1 is equal to A2 times V2. Where the area is small, the speed is greater. Where the area is bigger, the speed is smaller. A1 times V1 is equal to A2 times V2 is equal to a constant. Hopefully that's all right. You've also probably, if you've ever used a garden hose, you are probably aware of this. If you put your thumb over the end of the hose, you can constrict uh, the the opening of the hose on the end. You can increase the speed and get the water to travel further, right? It's just this equation. And again, this it's just coming from this idea that the fluid is incompressible. And for our purposes, water is incompressible enough that we're not going to worry about it. Uh, we're just going to assume that it's perfectly incompressible. Now let's worry about the case where we take the same tube, but we rotate it so that it is not sitting on the table anymore at the same height. Now the narrow end and the wide end are at two different heights, y1 and y2. And I intended y1 to go all the way up to here. Maybe I should fix that before we go further. So I intended y1 to go from this common floor, the 0 point, to the center of this tube. Likewise, y2 goes from, again, the common floor, R0 point, to the center of the tube on this side. And so I can remind you from our earlier in the semester that work is just going to go as quantity P1 minus P2 and quantity times V. I right related to force times distance, since pressure is force per area and volume is area times height, right, or length. Um, this will still have the units of work, right? If I look at this, the change in kinetic energy is just going to go as half mv2 squared minus half mv1 squared. And the change in potential energy is just going to go as mgy2 minus mgy1, right? But remember that the work changes the energy state of the system, and so the work that we do should be responsible for the change in kinetic energy and the change in potential energy. And so we can just set this to one side of the equation and the sum of these to the other side of the equation. That's all we've done here, right? We just took P1 minus P2 times V is equal to half mv2 squared minus half mv1 squared. That's just the change in kinetic energy, plus mgy2 minus mgy1. That's just the change in potential energy. We can remind ourselves that density is mass per volume. And so if I divide both sides by volume, this equation just becomes, well, the v goes away. I divide both sides by v, so the v goes away on this side. P1 minus P2 And on the right side, I have m over v in each term. But m over v is rho, is the density, right? And so we get that p1 minus p2 is equal to half rho v2 squared minus half rho v1 squared plus rho gy2 minus rho gy1. Pause the video here and convince yourself that you can go from this equation to this equation. Okay, hopefully that made sense. And then all we're going to do is we're going to group terms. We're going to put everything that has a subscript 1 on the left and everything that has a subscript 2 on the right. And if we do that, we get that p1 plus half rho v1 squared plus rho gy1 is equal to p2 plus half rho v2 squared plus rho gy2. Or that p plus half rho v2, p plus half rho v squared plus rho gy is equal to a constant. That everywhere along this tube, it is true that the pressure plus half times rho times v squared plus plus rho times g times y is equal to the same constant value. Hopefully that's okay. This equation is important enough that we should try to highlight it because this will be very useful to us in the coming days. All right. Hopefully that is not terrible. I would recommend going through this uh, until this stuff makes sense. These will be useful in doing your homework questions and also for the exam. So at the very least, make sure that you are keeping a formula log for yourself so that you have it at your ready when you're taking exams. All right. Have a good day and be well.